Aircraft materials, processes, and hardware. Metalworking process. The learners will be able to describe three methods of metalworking. It'll be hot working, cold working, and extruding. They're going to identify the different processes and purposes for each process and describe the difference between hardening, normalizing, and annealing. There are three methods of metalworking, the first of which is hot working. The second is extruding, and the last, but certainly not the least important, is cold working. Metals are hot worked from the ingot into some form and then either hot or cold worked to their finished shape. There are numerous processes for the hot working of metals. Soaking involves bringing the metal up to a specific temperature and holding it there for a period of time. Cooling, on the other hand, allows us to bring that piece of material down to a workable temperature. The quenching media is what we use to control the rate of the cooling. We can use oil, we can use water, we can use a brine solution, or you can just let it cool in just a still air. Hardening is a process of making the metal harder, typically going to be done by either adding carbon or cold working the metal. Tempering is what we do to reduce the internal stresses or reduce the brittleness imparted by the hardening process. Annealing produces a fine-grained, soft, ductile metal without internal stresses or grains. The annealing is the opposite of hardening. Normalizing is going to remove internal stresses set up by the heat treating process, things like welding or casting or forming. We want to normalize the whole part at one time. Case hardening is a process of making the exterior surface hard for things like crankshafts and cylinder walls for reciprocating engines. Nitriding and carburizing are two methods used to case harden. They're soaked at a specific temperature. The carburizing or the nitriding gases actually absorb into the material. It doesn't alter the sizes, but it does make the surface significantly harder. And then the last two are forging and casting. Forging is actually what you see here in the picture, kind of like the blacksmith forging a horseshoe. And the last one is casting, where we actually take the liquid metal and actually pour it into a mold like you would ceramics into a ceramic mold. When hot working, to be successful, the heat treating requires close control over several factors affecting the heating and the cooling of metals. Heat treating equipment, furnaces, salt baths. Some furnaces and shapes typically heat to about 2,000 to 2,500 degrees. The salt baths are going to range from 325 degrees to 450 degrees Fahrenheit. These are going to be used for, remember we talked earlier about soaking the parts. You could put it in a bath and you could soak it for a specific temperature for a period of time to get the desired effects you want in a metal. Temperature measurement controls. Accuracy of the temperature is extremely critical to the successful heat treating of metal. Soaking, the temperatures must be held constant throughout the soak. And then when we reduce the temperature, it has to go from the furnace to the brine in very minimal time, or it'll start to cool ahead of schedule. Cooling. The rate of cooling is critical, and we control the cooling rate by the type of liquid we use. The quenching media, as we discussed earlier, brine, which is a salt water, cools the fastest. Water is the second fastest, and then oil is the slowest. To reduce the chance of warping or cracking, we need to use caution when we're putting the parts into the quenching media. We want to set the part in cautiously, and then we want to agitate the liquids around it to destroy any vapors or any coatings and stuff that are forming around the metal, and to kind of keep the solution at an equal temperature. If you have irregular shapes, you want to make sure you put the heavy part in first so that it doesn't fall over, and then that could also mess up. Banging the part around could damage it during the heat treating processes. When you're dealing with clad aluminum, they also have a solution heat treat, but one of the things that you'll also notice is a precipitation heat treat process, and that's nothing more than just an aging process, just letting it sit at room temperature, and it will continue to get harder as we go along. If you remember, we talked about double D and D rivets, which are icebox rivets. we freeze them and hold them at a specific temperature, and then we drive them into cold state, and they sit over time, they'll get harder. That's a precipitation type heat treat process. Quenching equipment is also critical. Quenching, we want to make sure that our tank is the proper size so that we keep our fluids or our media at the proper temperature. The location is important. We only have a few seconds when we remove it from the heat or the soak and to get it into the quenching material. Temperature is important. We want to keep it within 10 degrees one direction or the other of the ideal temperature. The treatment of ferrous metals. It's critical to know the chemical composition to determine how to properly treat the metal. How fast do we want it to cool? What type of solution are we going to use? Again, the brine, the water, the oil. The behavior of the steel during the heating and cooling processes. What happens if we heat it above the critical temperature? What if we don't get it hot enough? The cooling, how is it accomplished under predetermined conditions? What are those conditions? These are things we're going to want to know. The speed, the rate, how fast do we cool? This is going to affect the hardness. And then the hardening. We need to remember, no matter what we do to a low carbon steel, you're never going to get it hard. Do you have to add carbon to it to get it to the desired hardness? Precautions to follow when hardening. You may need to put your part in a jig or a fixture to prevent it from distorting during the cooling process. The tempering process we talked about earlier is going to reduce the brittleness from the internal hardening process. It's conducted at a low critical point of the steel. You bring it up to a specific temperature. Again, we'll soak it at that temperature. You don't bring it above the critical, but you hold it to a specific temperature for a specific period of time. Once properly tempered, the strength will range between 125 and 200 KSI or 200,000 PSI per square inch. Annealing, we discussed, is what we're going to use. It produces a fine grain and it makes it a soft, ductile material. It keeps it from cracking or breaking when we're actually forming the metal. Normalizing is going to remove the internal stresses from the welding, the cast. It's going to be accomplished by heating it above a critical point and then cooling it in still air. Case hardening produces a hard, wear-resistant surface. Common forms of case harden in aviation are going to be carburizing and nitriding. Again, and we discussed earlier, we're going to use these for things that real common, crankshaft journals, cylinder walls, things of this nature, where you want the surface to be hard, but you don't want to alter the shape or the size because size is critical in some of these things. Carburizing. This is a form of surface hardening. Carbon is added to a low carbon steel by packing it in a container with charcoal or other material that's rich in carbon. Then it's soaked for about 1700 degrees. The length of the time you soak it is going to determine the depth of the hardening process. Nitriding is a similar process. We're going to put it in a special nitriding furnace. We're going to set it at about 1,000 degrees, and then we'll add ammonia gas. The gas is going to be circulated around the material, and it's actually going to absorb into the minute cracks and get into the metal. And as with carburizing, nitriding, the length of the soak determines the depth of the hardness. Non-ferrous metals, aluminum alloys. 1100 aluminum alloy is low strength, highly resistant to corrosion. If you remember from earlier discussions, that's 99% pure aluminum. Alloying is not the only way to increase the strength of pure aluminum. The other way to increase it would be to cold work. An O designation indicates that the material has been softened or annealed, and H is a designation to tell us that it's been strain hardened. Aluminum alloys are normally heat treated, not cold worked, to increase their strength. Although not always true. Remember, we're going to cold work some different types of D and double D rivets, and then we'll let them precipitate to get harder yet. A T4 and a W indicate a solution heat treat and a quenching. The T6 heat treated and then hardened to a specific hardened condition. Aluminum sheets are going to be marked to tell us exactly the heat treat process that was used on them. Here's some of the heat treat designations for non-ferrous metals. We reviewed some of them, but I'll give you a chance to look at them again. This is worth remembering. You'll see these again. Still hot working non-ferrous metals. clad aluminum, or L-clad aluminum as it's referred to, 10% of the total thickness, or 5% on each side of the aluminum alloy, is pure clad or pure aluminum. We put that on there as a protection to keep the alloys from corroding. Some alloys require time to artificially age at room temperature. We talked about this. This is precipitation type heat treating. Solution heat treating, I want to bring it up to a temperature of about 825 to 980. Notice this is significantly cooler than what we were heat treating metal with. Critical temperature is going to fall within 10 degrees Fahrenheit. We want to maintain that so that we get the proper solution heat treating. The time can range anywhere from 10 minutes to 12 hours. And the quenching media is going to be the same, cold or hot water, or we could actually spray the water on the material, depending on how fast we want it to cool. Reheat. Every time we heat a piece of metal to do a heat treating on it, some of that clad aluminum actually absorbs into the alloy. So we're going to limit the number of heat treats to 3. You cannot heat treat a clad aluminum more than 3 times, or you're going to alter the strength because we've added pure aluminum to it, and you're going to reduce the thickness of that corrosion preventative pure aluminum that's on the outside of the sheet of aluminum. Precipitation heat treating increases the strength and hardness of the material, but it decreases the ductile. Again, we're going to make it harder, but we're going to make it so that you can't form it quite as easy. There's a process that's also known as aging. As you let the material sit on the shelf, it's going to continue to get harder and harder. Typically, a couple of weeks is what it's going to take to reach full strength. We talked about the double D rivets where we heat them up to a specific temperature and then we put them in a freezer unit. This refrigeration process actually retards the rate of natural aging. Heat treating the alloy to elevated temperature and let it soak for a period of time depending on the material and the mass, and then cool in still air. So as we're annealing aluminum, we're going to heat it to an elevated temperature. Depending on the size, we're going to soak it. Remember that term, we're going to soak it at a specific temperature for a specific period of time. Dennealed parts are more suitable or more easily cold worked. Again, as we cold work these, we're going to mechanically harden them, and you may need to re-nail it again when the working process is finished. Heat treating of aluminum alloy rivets. 1100 rivets are going to be driven as fabricated. They're low strength and are non-structural. 2117 rivets are moderately high strength. They're heat treated once and anodized by the manufacturer. 2017 and 2014 D and double D rivets, commonly referred to as icebox rivets. Again, we're going to heat treat those and then we're going to freeze them, keep them in a freezer till ready to use, and then you drive them in the frozen state. They'll precipitate, heat treat, and they will get harder as they age. Most magnesium alloys are in a cast form in a solution or precipitated heat treated, and stresses are removed by elevating them to a temperature of 650 to 1000 degrees. Let them soak for a period of time, and this will help relieve the internal stresses on magnesium parts and magnesium alloys. So we've talked about working with this metal and getting it to a specific hardness. Now let's look at how we're going to actually test the hardness. There's a Rockwell hardness tester and there's a Burnell hardness tester. These methods are going to determine the success or the results of our heat treating process. They're going to tell us how it actually worked. The Burnell tester uses a spherical ball and it's forced into the metal. The hardness is determined by the diameter or the impression used, and we'll have a calibrated microscope so we can measure how much it actually penetrated. The Rockwell tester measures the resistance to penetration like the Burnell tester, but uses a dial attached to it. So this is a more common type, and we can actually look at the dial up. You can see it in the top right-hand corner. That top right-hand corner, and that depending on how much it penetrates, that needle is actually going to move. In the Barcall tester, this is a portable unit for softer materials like aluminum, brass, and copper. And again, this is going to just measure the hardness of the metal, how hard it is. How did our hardness process work? Did we meet the requirements we needed? Casting. Casting is formed by pouring the liquid into the metal or into a mold to get your desired shape. Extruding, on the other hand, aluminum can be done, we can actually pull it through a die. Most metal is going to be heated before we pull it through the die. During the extrusion, more metal is forced through a die, and then it takes the shape of a die. Aluminum is the most extruded metal used in aircraft. So you'll see wing spars and stuff like that are going to be made of extruded type aluminum. Cold working is a mechanical process. It actually hardens the metal. We're going to cold work it below the critical temperature. The strength and the hardness as well as the elastic limit are going to be increased on the metal. The ductility is going to decrease as the metal becomes more brittle, so the more you work it, the less ductile it becomes. It's possible that during the cold working process you may have to reheat treat the metal to anneal it so that you continue the cold working process or the shaping process. Two types of cold working processes are cold rolling metal, we're going to roll it at room temperature, or cold drawing. We'll cold draw things like safety wire or seamless tubing that we use for aviation plumbing. So in summary, we've reviewed the following terms and processes. We've looked at hot working and cold working. We've discussed that most metals will be both hot and cold working. We talked about extruding, how we actually force a metal through a die to get a specific shape item. We talked about the difference between casting, which is pouring a liquid into a mold, versus forging, which is like the blacksmith did, with the fire and the anvil and a hammer, and he would actually heat the horseshoe up to a red hot condition, and then he would actually get it to the size he wanted. We talked about the heat treatment of metals to include hardening, normalizing, and annealing. And then we talked about the hardness testing to when we're finished with the material, how we're going to test it to make sure that we've reached the soft state we were looking for or reached a hardness state that we're looking for.